Yes, we can start.
Okay. Good afternoon, everyone. Dear students, professors, all our guests, welcome. Welcome to the 7th event of the ArchiDesign Talks series for the spring semester. We have a valuable guest, Professor Dr. Ulrich Knaack from TU Delft, Delft University of Technology. Thank you, Professor Knuck, for being with us. It is our pleasure to host you. Before we start, I would like to introduce you briefly. Ulrich Knaack is a professor at the Delft University of Technology, Faculty of Architecture, the Netherlands, where he developed the Façade Research Group. He is also a professor at TU Darmstadt, Faculty of Civil Engineering, Germany, where he is the head of the chair of Façade Structures. Knuck has organized interdisciplinary design workshops and symposiums with themes like facades, high-rise and complex buildings, and is the author of several well-known reference books, articles, and lectures. I would like to add a few words from my side. I have been knowing Ulrich since 2013. He was the co-advisor of my PhD, which I did at Istanbul Technical University. I also had the chance to be part of his research group for 6 months in 2014 as a guest researcher in the Architectural Faculty of TU Delft. He's a very important figure in my academic life, so I'm very happy to see you here as part of this conference series. Thank you very much again. I'll be moderating the session, so please share your questions with us at the end of the presentation. In the questions and answers part, you can either unmute your microphone and pose your questions directly, or write your questions and comments on the chat box. Okay, now I can give you the stage, Ulrich. The screen is yours.
Thank you. Thank you for having me. It's actually a bit sad to not be able to be in Istanbul. As Sinem, as you know, I have a lot of good memories to Istanbul, having been to Istanbul very, very frequent for some years, being guest professor at ETU for a while, where we actually met with your other co-advisor or advisor, and we both remember the after show party after your PhD defense. That was a nice event as well. I really miss Istanbul. It's, yeah, nothing else to say. It's really difficult to not be able to travel right now. I changed now to this presentation mode, so I can't see you anymore. And if I have to do something, Sinem, you have to address it to me. You have to say you have to stop or something, and then I try my very best. Sinem asked me to do the Façade Roadmap thing, and I have about 120 slides. I'm supposed to talk an hour, so at some points I'm going to talk a bit faster. Don't worry. There's in the end a blog where you're able to enter all our knowledge, facadeworld.com. This is where we place all the things which we are doing. So if you're interested in certain things, just tick it in there, and you hopefully find what you look at. I used to start with this Façade Roadmap. It develops or sketches an outline which I did pretty much at the beginning of my academic career, defining which type of structures can we see developing. At that point, divided in a massive or solid structures versus skeleton structures, bottom part skeleton structures. Do you see my mouse?
Not now. Could you please move it?
I do. Okay. This is skeleton part, this is solid part, and at a certain point I thought I start defining what I think is going to happen in certain developments. And I identified some parameters from, say, my environment, which I believe were intensive impacts in our development. So oil crisis 72, 73 was something which brought our Western European environment to this point. We need to do something about the energy, which brought an intensive development in, for example, insulating glass facades becoming better in that environment. These aspects are interesting to see. And then the next thing is it's interesting to see that you can identify bubbles of people developing certain thing. It starts with this first generation glass. It's the 1840s glass bubble, which Paxton and Luden, which we all know from Crystal Palace, Paxton, which we all know from Crystal Palace, as one of the people moving the, at that time, very rural structural glass engineering towards a more industrialized structural glass engineering, not really being able at that time to identify the structural performances of the material. Super interesting to see. When we continue with this line, I tick the next box. It's the 1980s, 1990s structural use of glass, where we see all this first large superstructures in glass, all the glass fins, first spiders developing by Peter Rice. 1886, which brought us to this opportunity to create large, fully transparent, as we name it that time, fully transparent glass structures. Again, a bubble of people, and we currently in this situation of, as I define, a third generation of structural use of glass, where we see the Apple stores, Rob Nice doing his folded glass pieces. This one piece of, say, a deformed glass structure, the second picture at the left side, or the super solid glass bricks, which are on the super right side. Again, it's a bunch of, what, 10 people engineering this worldwide, which is then widely used in architecture, but the, say, key people really being able to engineer, that's a limited number of people. Really interesting to see, and also to see how they interact with each other, how they even sometimes bitch with each other. And then this energy crisis, as I named it, which gave us this impact of we need to do something with the insulation level of our glass structures, which starts with boxed window far left as a window with, say, 2 layers of single layered glass or non-insulated glass, IGUs, glass insulated glass units developed towards all the double facades, which we then saw till, let's say, 2010 as a development, and out of this understanding of the change of the building envelope, not only being the building envelope for rain protection and heat, but also becoming a part of the climate design of a building by also integrating building service units. This brought us to this next level of interaction, which is say, still ongoing development of integrating service components, the HVAC system, the heating and cooling system, into the building envelope, the glass building envelopes. And that's what this picture sketches, that some of these super high-end glass facades, double glass facades, are now ending with service units being integrated. This continues in more opaque structures when we sketch that, say, technology of facades, from solid brick facades to cavity systems to load-bearing light concrete, light brick structures changed, and adding the opportunities of service components into these, which we see in these first early sketches. The current, say, in my Western European environment, current technology developing is moving these opaque facades toward energy gaining facade systems. I'm going to talk more about that later in this lecture, but I wanted to make the broader picture out of this one. Again, this is a bubble of 20, 30 people really engineering it to bring it to a, say, technical level, which now delivers a certain energy impact. That's going to be chapter 1 of this talk, and then there's chapter 2, which is about 3D printing, which is, from my point of view, super interesting as well. Again, randomly picked pictures out of my environment, expressing that there's a development which we clearly see with all the different materials which we can print at a certain point, the polymers, the plastics, which we are used to, the metal, which is developing, the concrete, which we see a lot on Facebook and Instagram, the ceramic, more rarely, glass, very, very few, wood and paper, nearly none. And that's going to be the second chapter of this lecture, expressing the printing technologies and what we can do with that in our construction environment. So this is a roadmap to start with, and I jump to this chapter, this area of service integration into the building envelope. We are aware of concrete, light concrete being good for load bearing, but also for insulation, with the disadvantage of reducing the thermal mass, which may be an argument or an aspect to discuss. It all started, or kind of started, with this design school project in Essen. Design school is in a university building, which was designed by Sanaa. And they collaborated with Matthias Schuler, Transolar, a climate design, a very prominent climate design company in Germany, and Holger Techen, a very prominent structural designer at Bollinger & Grohmann in Frankfurt. And they were asked by the architect, can you please design a concrete wall, a single concrete wall, no insulation, so kind of impossible in Western Europe, no insulation, just a concrete wall. Tadao Ando like, as the quote, which can be used to that. And the engineers started working with that and came obviously with the solution. Now we either insulated at the inside, or we insulated at the outside, or we insulated somewhere in between. But still, the concrete walls are getting larger than the 20 centimeters Sanaa expected that time. And at a certain point, Matthias Schuler in person came with this idea of active insulation. Active insulation in this situation means that they harvest hot water from a mining which is below this design school. It has to be said it's an old industrial area with a lot of coal mining. This coal mining started changing surface of the ground by digging deeper and deeper, pumping off the water. Now buildings are built on this new surface, so if you would stop pumping the water, the surface would change again. The buildings on top would crack, and by that it's more expensive to allow the groundwater to get back than pumping the groundwater forever. And as it is coming from a certain depth, out of my memory, below 1,000 meters, it has a certain temperature. And this temperature could be used to heat something. And Matthias came with this idea, why don't we add a piping system to the concrete wall to heat the concrete wall, and by that actively insulate it against temperature from outside by just heating the concrete wall. Side note, yes, you can argue you could use this energy for different purposes, but in this specific situation, it was decided to use it to heat this building, this entire concrete building, and by that ending up with this super straight and super, say, static concrete surface, which is heated by this groundwater. That's an interesting change to get this opaque structure into an building service component. This idea was taken into account when Marcel Bilo came with his master thesis, his project in 2007. So you see, it's already a range or a development which you can see in time. He started adding these small capillary pipes, which you see on the far bottom right picture, the blue holes. These are 2 millimeter, 3 millimeter wide capillary plastic pipes being integrated, as we see it here at the top right picture, being integrated in a concrete surface, and this concrete surface then being heated or cooled depending on what you wanted to do with it. This was in the second project which he did, a small pavilion which was built. It's a polystyrol form with this 2-3 centimeter thick concrete sprayed at the inside, and by that being able to either harvest or distribute hot water, cold water, by that energy to the inside of this this building. This idea was taken by others. Rieder came up with a first idea of how to create a product out of it. And we talked to other partners, and this is, for me, one of the most important buildings in this environment, because it shows how such an idea could be taken by colleagues. Again, you can link it via friends and friends and friends, talking about it and then integrating it in their designs. Jens Schneider is the character who developed this factory building. It's an experimental industry factory building at TU Darmstadt. And as we see on the bottom left picture, they have this heating and cooling device being implemented at the inside and at the outside of the building, as well as the walls as in the roof. And by that, they are able to either harvest temperature and then store it by water next to the building and then deliver it to the inside of the building in wintertime, or they're able to harvest energy in summertime at the inside of the building, stored somewhere and then delivered to the top, to the roof, to the sky view at nighttime, which is what happens in this situation. And the making, similar to the projects Marcel did earlier, we see the capillary pipes, the whole thing being casted. Then we see the tanks to store the water. You can imagine the dimension which is necessary to do so. And then the delivery of temperature at the inside and the inside view as it appears when it's finished. What I really like with this project, it's a way of say, not balancing winter temperature versus inside temperature or summer temperature versus inside temperature, but the average temperature of that region, 10 degree, versus the average temperature of the inside, 20 degree. So we don't have to heat the entire distance. We don't have to cool the entire distance. We only have to balance the energy in and out via the entire year. There are free storage systems which are used to balance different levels and different speeds, but it really changes the way we can deal with buildings in the energy means. This idea is followed with other projects. Another project, coincidentally, in Darmstadt, where they started placing capillary system, a heating system at the inside of this remnant earth structure. It's a prefab remnant earth structure, super interesting technology to investigate as well, especially because of, say, the lower embodied energy which we need to transport these components. The final building nearly finished. And then there's another project which I like a lot, Jason Follen. Sinem, you will remember him. He was part of the research group who finished his idea of doing a decentralized solution of this energy harvesting device, which he ended up in his PhD with this component. We see the main section of a facade. Outside, we see the harvesting and distribution area with tiles and small copper pipes being integrated, and inside we see the heating device. And the bottom right picture, you see that white box. That's a decentralized storage, energy storage system, which well, will not overcome the year. That's too small storage, but may helps to balance a day or maybe some days, maybe even a week in the system. So you see that there's a movement, development from the first sketch ideas with the first mock-ups towards the first industry building, proving that technology works, and then adaptation in other places of how to integrate this into designs. This is a project which was done for a master student in Delft for India. He tried to identify climate situations and, say, main structure situation. Concrete, prefab concrete was in the end his target. And the middle large picture that shows actually the inside of this piping system within this concrete. This kind of weird forms depend on what's the minimum energy to transport the water within this concrete, and what is the maximum amount of energy to be taken of this water pipes within this concrete. And by this, this first chapter kind of stops sketching this next developments of, say, activated opaque facades. I may foresee it's either a service component being integrated into these facades, or it's, as I sketched it here, the full service energy. So this one, where we see that energy harvesting and delivery happens in this light structure as a system. We may also create virtual heavy facades in the means of material-wise having a light structure, but adding all this piping system. We hope to bring it technically towards building physics solid structure in the means of lots of thermal mass being given by the water being integrated into these systems. This is chapter 1, and as I started with these roadmaps, you can imagine then you start continuing with the roadmap. You end up in a roadmap for the structural or more solid structures. So you see all the different types of facades, which then end up in the just sketched opportunities, layout opportunities to develop new, broader, broader active facade systems. This is not about aesthetics. It's about, say, functionality of certain products, of certain components which can be brought into products, which then by aesthetic can be integrated into the design. It's more energy harvesting and distribution driven than in the means of aesthetic in this chapter. All right, this is chapter 1, and if okay, I jump to chapter 2, which is the 3D printing field. 3D printing came to us again via Marcel Bilo, a PhD who was active in that field. And 3D printing is either done, say, there, depending on which literature you read, you find 6, 7, 8, 15 different types of 3D printing. But it's mainly, you can divide it in 2 ways. So it's the extrusion way, which means you somehow press something out of a nozzle, and this nozzle is robotic controlled to create a certain geometry. And whatever you press needs to be either liquid or melted and then liquid and then hardened in a certain environment. That's what you easily can do with the polymers, plastic, what you easily can do with concrete and clay. We're going to see some pictures later. If you want to be more precise in surface quality, the binder jetting strategies are more feasible to follow. That means that you somehow place a powder, you place an energy resource, melt the powder, or freeze the powder by water, for example. Then you place another layer of the powder, do the same, another layer of the powder, and by that create a geometry, which is then in this powder bed, and then the powder needs to be taken away, and by that you get the final result. These are, as I say, 2 main principles of how we create 3D printing systems. This is one of the early 3D printing parts which I was aware of, far right. That's a soccer shoe of an UK scientist who at that time, I'm going to show a picture later of him, who at that time was one of the first investigating the, say, potential. He scanned his own food and then printed on polymers this soccer shoe which fitted perfectly to his feet. And by that was, say, the start of this product, which you now can buy by the common trademarks to do so. The middle one is another shoe printed, and far left, these are medicine devices being printed. Far left, a scan of one of my teeth, which was then reprinted, and the middle one for ears, replacement parts for ears. Obviously, in, say, these industries, a lot more financial power is given, so you're easier able to say gain certain developments due to the financial potential within this industries. But for our construction industry, we will see later, this is something which may be interesting. I always use this picture, which is a robot hand, and you see the white valves where air pressure is put in, and by putting in air pressure, this robot hand starts to move. So it really grabs your hand and really can feel it. And if you start pressing more intensive, the air pressure gets higher and it starts to press back again. Why I like it is because you're all aware of how such a robot hand would look like when you really engineer it with all the springs and wires and screws and metal sheets to be created. And here it's printed in one go, and if I remember right, polyurethane. So it's a lot simpler to develop something like this in one piece, which then is manufactured in one component. That's the interesting thing with 3D printing. I like these chairs, very early chairs from Marco Hemmerling, somewhere around 2010. And the middle one, that's a one-to-one structure of a 3D printed force optimized chair for a person to sit. The far left one was an print, which was then transported in a container and by that overheated. It directly expresses the problem which we have with polymers being printed. If they're getting too hot, they start to melt. And the far right one is an interesting one. It's a so-called Tango Material. So it's a printing process which allows you to print either soft or stiff material in one process, different materials. And by that you can create this structure as it is designed here. It's the same chair as the middle one, but it shows that, say, the place you sit and the place you lean, the black part, is more weak. So it allows you to shape to the body, while the rest of the structure is more solid. And by that, withstands structures a bit more. Then the naughty part is the far right picture is a 1:5 or 1:10 scale, while the middle picture is a 1:1 scale. So it defines directly that the dimension of the printing room is something which is super important for these designs. And then I go to this slide. It shows one of the early developments in the 3D printing. Dus architects and Dutch colleagues wanted to print in Grachthuis, a house in Amsterdam, which is close to a small river, and they wanted to print it entirely in plastic. And he was able to convince all these leaders at that time that the 3D printing somehow is something which could become important. He was doing it in polymers, which are not good for structural use, so fire and UV becomes a problem. So in the end, it didn't work as they expected, but they say they prepared the ground for us to continue these technologies. It goes on with this Gartner hype chart. It shows these are the top part of the wave. These are the, say, technologies which are emerging. This is what we all think is going to be super fancy. And this is then the valley of disillusion or disappointment. This is where technology shows that things are not always simple. And it's super noisy. I have to close the door. Just a minute. Back again. So concept starts here. We have a good idea. We believe something is going to work. Then we start really digging into, and you're going to see samples of that. And we learn things are getting complex. And after some years, you really end up in products. We're going to see some products here as well. And the interesting thing is, out of experience, say from the top point till you really get to product, this is a range of 10 years, kind of. 1 or 2 PhD generations, which are getting into, till you come to that point that you really see products developing well. Interesting experience. I start with these sun shading devices, far right, developed in Delft, a click system out of polymers, which was designed to be added to an outer surface somewhere at a position where you identify this is on the globe, the position, this is the shading angle I need. You get something printed, you click it together and place it in position. UV becomes a problem, which brought us to this OCA 3D project, which is an IGU, insulated glass unit, with some three-dimensional printed structure, which is designed to be say perfectly oriented to shade for the situation this glass panel is placed. This continues with the solar thermal harvesting idea. You remember the energy harvesting I showed earlier. These are 3D printed, polymer 3D printed bricks, which are supposed to be harvesting devices for solar thermal energy outside. And that's another experience which you make with these printing. They printed bricks. The bricks needs to be connected. That was kind of impossible, so they started to develop their own printer, which in the end was able to print 2-3 meter high components. But you see the dimension of these volumes which are printed, and then production speed becomes a problem. They in the end needed 10 days to get one of these components printed. Yes, this is pre-industrial research, so if you really need to get forward to that, you may end up in more high-speed oriented production processes. Brings me to concrete. This is contour crafting. Colleague Kosnevich from Los Angeles, somehow 20 years ago, started developing this. It's actually extrusion process, which we see in this middle picture. It's an extrusion process of concrete. You just print the concrete out of a nozzle and place it. He is the one who developed this as an idea. If you go to YouTube and Google contour crafting, super nice videos to see. It didn't work out at that time. Industry wasn't ready, market wasn't ready. He talked to Caterpillar, they laughed at him, and at a certain point he stopped. Some 10, 15 years later, this happened somewhere in the media. Chinese company took these ideas, started to develop it, and actually printed prefab components. So what we see here is this is a prefab component, which they printed horizontal and then stapled. And that was the point when things changed, then others identified this is something interesting, which brought these two players into the picture. And the top one is going to be important for the next slides as well. It's TU Eindhoven, which came with the first 3D printed bridge. And it's actually, again, horizontal printed, then vertical installed units, another unit, then pre-stressed. So it's like a staple of books, which you pre-stress by power and then are able to place it in a certain position to allow loads to get on top of it. They have a nice device, which we see here on the far left side, size of people. This is the printing room. So the size is less an issue. They have this Portakran system, which allows them to move the nozzle in position. It does not allow to tilt. That was a problem. And then they started printing all these different layers. And we learned a lot about how to control the dimension of the extruded concrete. Because if it's just round, it's maybe simple. But if you start to do edges, curves, this may become more complex. Tilting concrete, that's something which gets more complex as well. This technology developed a lot. There's one small sample which was done in my environment, is this turtle. Chris Borg learned how to use that nozzle in Eindhoven to create these forms, these free forms. Super interesting research. And this is the current status of 3D printing. ETH Zurich is doing a lot in this environment. Then this is TU Braunschweig in Germany. They do they spray concrete with this robot-controlled system, and this is Peri, and mold system supplier, who understood that the 3D printing could be an interesting field for them in, say, that 3D printing environment. And this is where we are. We're currently at, say, a number of universities, a number of research institutes being active in 3D printing, really bringing it to the next level. Still, the reinforcement in this 3D printed concrete is an issue, because we may add small steel fiber to the concrete, but still larger components are difficult to handle, and intensive stress forces in concrete, not that simple as a problem. This continued with this one, which I like very much as well. It's an concrete, a spin-off from TU Delft in Rotterdam, and as the cathedral in Paris was burning down, they said instead of rebuilding something out of the original material, why don't we take the dust and combine it with cement and reprint certain components, which is, say, in the beginning of a nice story. It may technically will have some issues, but it shows the opportunity, the free form opportunity these material may deliver. I move forward to the next material, which is bricks. And Langenberg, an artist from the Netherlands, once came to me with these small components, and then understood what the potential of 3D printing clay and brick could be. He started with this more art-oriented object. I found other colleagues, Sita in Copenhagen, doing this. I found another colleague in Hong Kong starting to do these free-form components. friends in Guimarães in Portugal started to use the same 3D printer we bought, and we bought this small device. It's a portal crane system, which then was our first 3D printer for bricks. We continued shaping the geometry, and you can imagine in the normal production processes, bricks are extruded. So it's this extrusion process which has one shape, and you can only change length of the component. You can't change the geometry of the component. And by the 3D printing, you may be able to really come to entirely wild shapes like this one, impossible to be extruded as a system. We changed towards a typical roboter arm driven device, which we see on the left side, and we're currently running, I think, 3 of these devices on the 3D printing of bricks. What do I want to reach? This, I'd like to create a brick which has the geometry which I want. The surface I'd like to get quite aesthetic. The technical performance integrated like this solar radiation and solar heating devices, some thermal insulation, which means it has to be light in a certain area, and some solid parts which would be load bearing. This is a gypsum brick sketch idea from Dennis de Witte, who started developing it towards these bricks, and give it another 2 or 3 PhDs and we're going to be there. It's going to be interesting. I move forward to the next type of material, which is metal. In this case, aluminium, laser sintered aluminium. So this powder bed system, a powder bed where you then with the laser position and melt the metal powder towards a solid piece of metal, which in this first project was the idea to create a free-form geometry component. We'll see that later again. This is one of these components which was then by Alcoa, a company at that time interested in this activity, brought into this free-form facade stick system. When you have a stick system, rectangular stick system, and you want some kind of wild angles, the dimension of the saw defines how wild this angle could be. And if you really get 3-dimensional, then it really gets complicated. The alternative is you cut it rectangular and print the knot as a component. So then this one knot solves these problems, which is a geometry problem, and B, more technical speaking, for the facades, and say drainage, water drainage question within this system. Others continue with this idea as well. Arup Amsterdam, she was the first printing this free-form structure. This is an pre-stressed tension compression structure, tensegrity structure, where she either right side would have a simple metal part, or left more advanced and lighter by its construction. We did some engineering and design development in Delft. This is first metal node which was done in Delft. It's part of this free-form geometry. The student needed to stand on top of it, and when we look at it, we nicely see how this powder bed system works. You see there's this one layer of powder bed, then it's melted, then there's the next layer of powder bed, and the next and the next, and by that this geometry appears as a setup. Another one, a PhD in Darmstadt, who continued with that one, and in the end developed this free-form facade system as a product which is now available with some companies named here, Imagine Computation, Rosmanit, Kegelmann, and Vicona as a system supplier to be used in facade construction. So after the first PhD, some 6-7 slides back till now, this is a range of 6-8 years till we come to the point that we are able to deliver something into the market. It continues with a stainless steel version of the same concept, ODS Janssen, ODS in the Netherlands, Janssen in Switzerland, which are following this line and creating a free-form knot for their stainless steel system. Some other disadvantages in the means of drainage and leakage, so different setup, which needs to be developed. After the laser sintering system, the laser extrusion process or metal extrusion process needs to be defined. This is MX3D, an artist group from Amsterdam. They simply, top picture, they simply placed a welding device, a welding gun on top of a roboter arm, and then controlled this roboter arm to create a certain geometry. And they're doing super nice aesthetic. They started with this idea of really making a three-dimensional geometry, and currently is in the, say, finishing process of this 3D welded bridge to be installed in Amsterdam on top of one of these grachts. Super nice, nice design, and it's interesting to see also aesthetically what this technology delivers. So you see how this welding process opens and stops and creates these voids and allows to really shape this this geometry according to your technical needs, if you want that, or your aesthetical needs if you're interested in that one. Really like the the way they deal with this as artists / engineers. This is our welding devices in Darmstadt, 2 roboter arms, the red ones with welding guns, milling device is the gray one. This is how we started. You see all these voids in the structure, not very much pleasing. You get more 3D geometry, and in the end you may even end up with these lattice structures. So you easily can combine these structures and these structures according to your technical and aesthetical requirements, following the say technology and allowing to have this certain appearance as an outer geometry. A project we did was this small bridge. The interesting part in here was the bridge was not done vertical as components and then weld together and installed, but entirely horizontal. So the welding device, the welding gun, was trained to do a welding process which allows to have a horizontal welding line. That was a tricky one. They found a good way to do that, and by that ended up in this nice little object to be shown. This is another one. It's an spider-like fingers which keep facade plates in certain position. The idea here is to instrumentalize this technology towards a set where you scan a certain geometry of a existing building, you design a new facade in front of it, and you develop digital the placeholders, distance holders in that way that they are fitting at exactly one place, and you don't need to adjust any of this, which makes it interesting for the steel manufacturer or for the facade manufacturer to build something without any tolerances directly in the first shot as a setup. I really like it as an say principal concept. Printing glass project already 10 years old. Lisa Ramek started with this first printed nozzle on top of a glass sheet. The idea becomes is clear. You either fix something on top of this glass or you fix the glass by that. Then we see the colleagues at MIT doing their first melted glass components. The difference here is this is melting glass on top of a piece of glass. A lot of thermal stress appears in that. So it's interesting to handle, let's say it so. This is only glass on top of glass, so there's a less thermal stress which needs to be handled, but they were the ones which say created the largest device to do so. Another company doing something similar, QSIL, a Dutch company, doing it on a more nano scale. And then engineers in Darmstadt continued investigating what really happens when you weld glass on top of glass. And here again, you see my mouse, there's a small void, which obviously say from the structure point of view for the glass is something which you'd like to avoid as a conclusion. What we want to reach is this kind of systems, top part, fixing devices to keep glass in position, bottom part, readjustments or reinforcement of glass as a general structural layout, which then, as you can imagine by these pictures, also can start becoming an aesthetic component. When I go to polymers, we continue with this one. This is interesting. The large picture, that's Stratasys. They do a nice tango-like material. So they have either rigid parts, which are the white parts, or different show values, so weaknesses of the structure, which are the black parts. This is basalt fiber reinforced plastic. So it's actually reinforcing like concrete, but in plastic. That's also something which could be an interesting solution. And then we come to the next one, which is printing paper. These are the first 3D printed paper parts done by a PhD in Darmstadt, which currently is quite good in position to create the three-dimensional printed geometry of these paper structures. You have the liquid paper pulp, which needs to be extruded. It has to be dried in a certain quality, and you need to make sure that the shrinkage ends in a setup which you're really able to control. Continuing with this, obviously wood is something which was missing. And here I'm talking about real wood, so not wood fibers being combined with 60% polymers glue, but pure wood being made liquid, so separating the lignin and the wood, getting the whole thing liquid, and then combining it to become a piece of wood. Yes, we have aesthetically not yet any idea of how to solve that it really appears like wood, and yes, we don't have yet a technical solution, a technical request for this material to be used. But I wanted to browse through all the materials which are, say, in general possible to be printed. I continue with some general outlines about 3D printing. So why do I do this? When I do my typical building technology education, the target is to teach about how you make certain things. And the consequence of making things is you need to be able to assemble it, and meaning to be able to assemble it, this defines dimensions in structures. And these dimensions are given. When we think about 3D printing, we can design something not construction oriented, so how to get it together, but function oriented. What does it need to perform? So where do I need which material for what purpose? And then I can theoretically define how this material is to be placed. I take this bottom right picture, which is a three-dimensional stick system. And you can see by being sealed with silicon, super prominent architects, super bad detail. By being sealed with silicon, this is obviously going to leak. There's no way of not having this leaking. So this is construction oriented, but they wanted this geometry to make it better. You need to create a different geometry here, which may ends up in this kind of freeform structures as a first setup. Then second thing, and that's something which I think is also very interesting for our industry. It's a very fragmented industry with very, say, small suppliers of systems. So an average, or say the larger system suppliers for facade systems in Europe have the dimension of a small car industry supplier in Europe. So they're rather small, and all manufacturing is done in smaller industries, mainly in, say, close distance to the construction environment, and that delivers that we are dealing with a very fragmented industry. That's the one part, and the second part, we are dealing with an industry or a construction environment which requests one-off solutions all the time. And this is where this nice gentleman, Neil Hopkins, comes into picture. He draws this sketch saying, if you're ending up with products less than 10,000 in industry, additive manufacturing may become interesting. This is very broad. Different materials do have different numbers of that, but you can imagine that in our construction industry, not always dealing with 10,000 or 1,000 of the same components. We need them individualized, and this is where this 3D printing is an opportunity to be used as well. Then this one, solutions for refurbishment, components which you can't buy anymore because they're out of stock. They're not in the shelves anymore. They're not produced because the company went bust, disappeared, whatever. This kind of components to be replaced, that's something which could be also an interesting way of doing certain things. And then this one, which means additional technology, additional functionality, integrated technologies. It may be the energy harvesting as a solution, but also may be other technologies. And then this one, which I liked a lot as well. Coincidentally, I was brought into this project where they scanned an inner part of a very prominent museum in the Netherlands, Mauritshuis in Den Haag, and they identified that color we currently see are not the original colors. So an art historian defined the correct colors of the origin. We scanned the surface and we reprinted a part to express how it looked at that time, which you then can imagine making it broader, making it more advanced, bringing it to the next level, means that you can mimic a certain place at a different place. So if Venice is dying, we may reprint Venice next to it and keep the old one existing. Technical handling of this is not simple. So the scan I show here, the right picture, that shows the geometry and the colors which were scanned at that time in wrong colors transfer. But it appeared that, say, the handling of this data, that's something which is interesting to deal with. And I learned a lot that the digital model to be done well is very important to be then able to do the digital, the analog model as a reprint. Small merchandising block before I finish. This is the Beam homepage. Beam build environment additive manufacturing. We do run a conference which is happening twice a year. And we have this nice exhibition at the Formnext trade show. Formnext is happening in November. So next November, second week of November, there's the next Formnext show in Frankfurt. The interesting with this is they actually double their size every year. So it's in the trade show doubles its size every year, which means it's really in very much boosting technology. And when I went there first in, can't remember, 2018, 17, 18, it was mainly plastic. When I went there 2020, 1920, it shifted towards metal a lot as production technology. So there's say a clear shift in quality and material technology to happen. Closing this chapter with this slide which I showed, all the different materials which we use: polymer, metal, concrete, ceramic, glass, wood, paper, and the roadmap where this is all to be placed. I finished now, and as I said, maybe too much information, but you're very welcome to check this homepage, Façade World, which we use as a scientific outlet, which shows all the projects which we do, which shows all the publications which we do, where you find all the PhDs. You also find a picture of Sinem there with her defense as an activity. And by that, I would say a bit less than an hour, I stop.
Yeah, great. Thank you very much for this great presentation. It was definitely inspiring. Now it is time for the questions and comments. Let me check the chat box. As I see, there are no questions written. Maybe they want to pose this directly.
Am I interrupting you?
No, Hocam.
Okay. First of all, I'm sorry. I'm really sorry to miss to welcome you in the beginning because I had a technical problem in attending to this seminar. Thank you very much, Uri. It was really very interesting and inspiring presentation for all of us. I would like to use this chance to ask my question, if you let me. Yeah, Hocam.
Yeah, of course, Hocam.
I'm really very curious, very much interested in the design process of geometry for free-form components you have mentioned. So what sort of process do designers follow to figure out or end up with this certain geometry? Because the morphology of the geometry is very difficult to understand prior to print out it. So what sort of design process do designers follow prior to end up with this certain geometry? Is it a kind of trial and error process, or do we have a chance of using any software in which we may finalize the end up product by means of testing it digitally? I mean, are we really testing our design with analog model in the end, or is there a way of being sure of our design in a fully digitally designed process. Thank you.
You're very welcome. It's a emerging technology, so for sure there's no end yet to see. That's always when we look, say, in architecture, in construction industry, how technologies develop and what time they need to unfold their full potential and their full power. We are pretty much at the beginning of this, so there's going to be an interesting journey to come, and the more we're starting with this, the more people are getting inspired and start their own activities. And as you all know, these plastic printers you now buy for 200-300 euro. You may even buy the set for 50 euro somewhere in the internet and print your own parts by your colleagues and then rebuild these devices. So we're going to see that change. And we're also going to see that change in the construction industry. When we see all these components and we call them, for example, structural optimized. Yeah, when I talk to my structural engineers, structural optimized for what question? Is it main loads? Is it payloads? Is it additional wind loads? Is it additional earthquake? So if you add all these components, then they end up looking rather solid. So you may have to make decisions to direct certain forces to certain direction. So you may have to start funneling the structural design process towards a certain geometry which you like. That's the same with other technical performance like the building physics or the water, as I showed. And it also has to do with, say, the aesthetics which we like to do. I really liked a step they did in Eindhoven at one moment when they identified that the concrete always finds its way to somehow flow close around where it's supposed to. But if you organize this, you actually get certain patterns implemented into these structures. And then really becomes aesthetical attitude as well. And that's something which you can't really do with the algorithm, which you then have to experience. So you start experience with these aesthetics, and then you implement the experience of your preferred aesthetic into the algorithm as an activity. So say, speaking for the designers, I'm not worried at all that we're not going to do the design ourselves because it's another tool which helps us to manufacture to certain quality. We experienced the same with the CNC milling some while ago. When the first CNC milling devices appeared, people felt like, okay, this is going to be against craftsmanship because craftsmanship is not needed. I mean, you just mill everything. Now, yeah, but you still need to somehow connect these pieces to your mill. That's the same with these devices. We're not going to see 3D printed houses in a larger range than the experimental. We're going to see components of houses being printed, but an extruded brick is so cheap you can't even think about printing it. It's just completely off of the range. So some complex parts of the brick building that will be printed, but the less complex main parts of the building, that's going to be a classic extrusion bricks. That's the same for glass. That's the same for aluminium. So it is another technology. It's not the only technology. I'm just showing this as one chapter. There are 10 other chapters which are interesting. It's just one chapter which currently say has the advantage of having a nice sex appeal for future PhDs to join, has the advantage of being interesting for industry to be investigated, so they pay the PhDs to do so. And yes, I can also pose in this situation, but it's one field. It's not the only field. Also to be clear about that. You notice I'm not a software specialist. So yes, there are all these nice softwares, and every 2 months there comes a new one, which is delivers another plugin which you add to this Rhino system, and then they come with a different angle. What I see as, say, the main target is next to the technology which we're now getting control of is what additional functionalities are these systems valuable for, and what does it aesthetically deliver? And that's a nice exercise for design school.
Thank you very much.
It was a long answer, huh?
No. Understandable. Thank you.
And any other question? Maybe Ulrich, you can also stop sharing your screen and see the.
I apologize.
No, it's fine.
If I may ask a question for Dr.
Yeah, sure.
Thank you.
Yeah.
Hi, this is Bengulu Engin. Very nice to meet you, even if it's virtual. It's a pleasure. My question to you is about the thicknesses of the walls that you actually showed, and I couldn't help but notice that there is this increase in thickness, and it struck me that in old times when structure was important and the facade was actually structure was part of the facade. And then with the modern movement, we got these thinner and thinner walls when the structure was a framework. And now it seems that we are again kind of thickening the facade. Is this a trend that you see continuing? I mean, do you agree? I see you shaking your head, so maybe you don't agree.
You're asking a complex question, man.
Okay. Is there a simple answer?
No. And what does Eurydice always say in this kind of? It depends. Yeah, fair enough. The aluminium, steel, glass systems they developed intensively. They're so good. They're so say technically advanced. They're tweaking the 0.0.0 something numbers for the U value or the G value or the FX value or whatever. So that's quite advanced. What I did here with these 3D metal knots, I helped to get this one small problem of getting a more freeform geometry, which is a small percentage of projects really having as a problem. Okay, another level of advancedness, which is to be continued. It's always argued that we love, especially in cities, these stick systems because they are so narrow by size, and by that are still performing in a reasonable U value, which makes more lettable floor space. These are really the arguments I hear by developers, investors when they build buildings to narrow this. The ancient solid structure, yeah, it has its benefits. It's say technically less advanced as building, but more robust as structure. So you see also that some designers and engineers being interested in less technical, also taking a different position, are taking this into account and trying to develop structures which are less complex made and having smaller windows. So, for example, in your climate situation, having the full glazed facade doesn't really help that much. You have to shade it a lot. So it's an aesthetical position you take, which you then have to defend with shading, versus a more solid brick or concrete structure. And here we talk about the solid one and not the super light extruded bricks that may building physically help as long as you still gain enough light. This wouldn't work in Finland. They're more interested in harvesting more light, so they need to have larger windows, and they actually need to have lighter structures to be able to be more flexible in their production. The difficulty is that we have so much energy so cheap that we actually can overrule all these building physical questions. So we just cool our two large glass facades. And that's the point where it really gets tricky. So how long can we really hold this? You see the energy crisis, the energy prices raising in your country as well as we do. And so even if we are maybe not forced by law entirely, we still see that happening. It depends pretty much on the climate, what kind of structure would be the best, and not on the technology.
Yeah, thank you very much for your answer. Thank you.
Thank you. We have questions from a student, Halima. Halima, you can ask your question.
Hello. Hello. Thank you so much, Ajahn. It's really a pleasure having you with us here in hopes of having you physically at our school someday. My question is, I don't know if you've answered it and I've missed it, but I'm really concerned about this technology, if it's going to drive us into a future where the costs would be efficient and not high, or this technology could do the exact opposite and maybe drive the costs higher.
Costs are not
So,
related
yeah.
to technology in this respect. Costs are related to prices of land, and prices of land is related to average income and what you can afford. There's not my discipline. There's research done that an average European family pays 15 to 18% of their income for energy. And it doesn't matter if they live somewhere in Spain or if they live in Norway. That's an average number you are allowing yourself to use for energy. Some may less, some may more, but it's an average number. And so you either don't need a lot of energy, but then it's more expensive, or you need a lot of energy to heat up your place, then it's cheaper, like in Norway. So the costs of construction, that's partly related to the materials, but it's also a lot related to the environment you're working at or you're living at, and then what is accepted to be paid for. And the cost in Istanbul is a different story than the cost in Izmir due to the location. It's
Great. Thank you so much.
Technology is not going to solve that.
Thank you. And Devrim Hocam, please.
Hello. Good evening. Thank you very much for this valuable presentation. So the 21st century architecture is also named as the architecture of potential, or spoken architecture, as Peter Eisenman calls architectura parlante, let me say. And so I do remember an interview almost 30 years ago with Rem Koolhaas. He said that especially the architectural facade of megastructures, public buildings, should be evaluated or will be evaluated independent from the building as a multi-phase layout. So not only an outcome, as a technological outcome of the engineering performance. So that should be evaluated independent from the building. So kind of an interface, having a strong dialogue with the citizens, with the public space, and etc. So what do you think? What will be the role, the mission of the architectural facade in the future? Thank you very much.
Do you want a long or short answer?
Longer than
the longer the better.
Longer than my
Rem Koolhaas, that's an interesting character. That's really an interesting character, and also the way they changed their position as office in the last 30 years. Really interesting to see. I understand this comment. Yes, the building envelope is not only having the function as a building envelope, which means wrapping the building and making people warm and allowing them to view to the outside. It's also a position to the city, no question. Nothing against that. That's absolutely correct. And building envelopes are measured by that as component, and depending on the importance of the building, the position of the building, they either get more awareness or less awareness. The Dutch have this nice committees which have to decide the aesthetics of buildings to be built in a city. It's actually a well-being kind of commission. Welstandscommissie, that's the name. It means more a well-being than an aesthetical. So it's seen that there's this new buildings have to have a certain positive impact to a built environment, and all architecture, also the very less important one, all architecture has to go through these committees in Dutch cities. And you can imagine this also becomes a political thing. I don't like that architect, I argue against his facade, blah, blah, blah. That could be also a part of this story. The interesting thing with Rem Koolhaas and UN Studio, when you see Kunsthal in Rotterdam, I really like that sample. It's one of the early buildings. It's technically it's a super cool, nice design, absolute aesthetically absolute perfect. Technically very limited. And he said at that time, if you don't have money, you don't get details, and it's not going to last long. So if you have half the money which is necessary to build a proper building, you're going to get a building which is going to last half the time. And it started leaking after half the time. So the details were simple, the materials were simple. He used it very well, very good, but it lasted not that long. Unfortunately, it was such a nice building that the Rotterdam people liked it so much that they needed to refurbish it to a certain level. That happens. Cut. Then I see his Biennale exhibition about technologies, and that's an interesting one because there all the traditional technologies and the modern technologies were actually catalogued and brought together, and he really brought it to the point that good architecture relies a lot to the detail you do. That was really interesting experience through all the technical components. And he didn't do a design exhibition about super cool, fancy, whatever designs. He actually made an exhibition about technology, how to make architecture. So I understand his position for the city. I do follow it, but I see also a shift in understanding technology being implemented in architecture at that office. And what they currently ask when they come to Delft, they say we don't need more designers, we need people knowing how to make things. So that responsibility appears in their work as well. That was a bit longer than your question.
Yeah, thank you very much.
Thank you, Ulrich. And the next just question from my dear friend Mine from Bilgi University. Hi, Mine.
You're muted, I think.
Yes, sorry. Yeah. Hello, everyone. Thank you, Ulrich, for the presentation. I wanted to say hi and thank you, Sinem, for inviting me to join as well. I do also have a question. I'm joining here on behalf of Istanbul Bilgi University today, and we have a very similar course dealing with facade design this year as a special topics course with fourth-year architecture students. I'm not sure if any of our students joined the session, but on behalf of them, I want to ask you, what would be your insight as a starting point in the facade design? Because we have so many things to consider. Even in your presentation, you showed us a lot of different technologies, a lot of different techniques. At the end, it comes to a balance between the form and the function. So it becomes a really complicated issue, and everyone has a different perspective. So as a person who knows you and also as an interested party, I wanted to get your insight about this.
Mine was, as Sime once guest PhD in Delft. And yeah, you're continuing your PhD, and every now and then talk about that. I gave a rather technical presentation, and you read me also. The deeper I dig, the more technical it becomes. But in the end, if you consider doing facade engineering or facade design, it's and one of the key aspects. It depends pretty much on your personal emotion and what you really are interested in. I clearly remember when I was doing this decision about doing a PhD in the structural use of glass and doing a roadmap of glass structures. That was a pure emotional decision. It was a kind of unknown field, not only for me, but also for the others. And it needed someone drawing a map out. It feels like you're conquering a continent you don't know. So you pack your backpack and you just start, and you hope there are no crocodiles you can't fight. And at a certain point you just start, and then you have your personal interests. You're interested in the environment, you're interested in a certain material, you're interested in a certain function, and that say gives you an additional aspect of how to start. And then you start, as the two of you did your PhD, or do your PhD, as you know, it gets broader and broader and broader and more and more and more, and yeah. Then you have to make a choice, and you have to narrow it down to something which keeps it possible to handle, because otherwise it's infinite. So we could go in this facade engineering down to total detail. My colleague in crime in Darmstadt, he's a glass specialist. He's an absolute nerd in understanding how fast cracks are going in glass. And you can imagine what deep, say, material knowledge they need to have that material glass, which is a frozen liquid, and understand how these cracks behave. He's a total nerd in that. And so if you're digging for this direction, be welcome. If you want to go into the, say, global, what type of facades are making sense, what kind of climate, that's an entire different story. Then you're entirely off of this material level and you may drift into this energy level. In the end, it's a personal choice. What I can advise, and that's say the background of your question, it's a quarter of the building turnover. So if you go for commercial buildings, a quarter of the budget goes for this. And that's nearly the same as structural engineering. And there's very rarely education, and there are very limited specialists. So you for sure get a job.
Yeah, that's also a nice motivation.
Absolute. You may earn more than some of your classmates. Yeah.
Thank you for the insights.
Thank you, Mine. The other question is from another student, Sevgi.
Hello. First of all, thank you for this really creative and informative presentation. I would like to ask you, are you creating these algorithms the way that you want the building exactly to be, or in some parts do you produce some alternatives in different methods, not this kind of algorithms, to prevent some disadvantages of the structure, for example, overheating, or the stability of the structure itself, the thickness of itself?
We haven't found a solution to do the overall algorithm which hits it all. So I talked about this, say, structural design part. I talked about this interesting developments which I see in aesthetics. We are in the development for the, say, thermal parts. We haven't even evaluated well these free-form bricks with all its functionalities. It's still a sketch. So there's a, say, gut feeling that this is correct, but it's not yet evaluated because it's it still was too complex till now. We are still scratching the surface for the manufacturing of the materials. So that level will come. And also need to identify where would I find finance. So brick manufacturers, they're not going to, say, invest deeply into these systems as long as they can't prove them there's some technical performance which they can sell better. And so it's this balance between the technology which we can control, the research interest which is also given by the market, and the capability we are dealing with. So there's no multi-algorithm which hits it all. And I have to say, I don't believe that I will find them ever.
Thank you.
Because if we solved most things, something new appears which could be also interesting. It's infinite, which is good. Good for research.
Yeah, infinite. Yeah, thank you.
Any more questions? Edip Hocam.
Okay, thank you very much for the nice presentation. I have a just small question. So approximately, I would say 15 years ago, as timber was very, how can I say, common also in the research field and so on, there was a problematic issue in production of the CLT panels. So that means the gluing of the layers it was not very easy, and just large scale industry could somehow deal with it. Do you see the same danger also for the 3D printing? Because you mentioned also these SMEs, that means small and medium-sized enterprises, which
Absolutely.
might, okay.
Absolutely. I totally copy your comment. Yes, and the CLT thing changed a lot. The glues developed intensively, so that say industry adopted all the digital controlled machinery very well. So it's actually a good sample of an industry which developed intensively with this CLT cross-laminated timber. So layered timber layers on top of each other. And it's interesting to see how this CLT story changed the, say, normal original wood towards an industrialized wood. And yes, in these processes of elevation, you always have failures. Absolute sure. No question. Absolutely logic, and that's going to happen with the 3D printing as well. Okay. So absolute, it's going to be disasters coming, no question. You have to make sure that no one is harmed. Yeah, that's how it is. The steel bridge I showed from Amsterdam from MX3D, super nice object. Structurally speaking, not that advanced. It's a lot of solid structure. So yes, they can sleep well. Which is a good one, because it's going to be a public bridge. It's not going to be controlled at nighttime. There's no one going to take care of that. Not someone crazy is doing something wild with it, and it may be hit by a boat. So it has to have a certain structural redundancy to not harm someone. But for all the other parameters, now we go as far as we can to see what we can reach with these systems, and it's not going to work at some places. Absolute. Yeah, that's evolution, which we are nicely allowed to do in architecture by being paid by others to do so. That's yeah.
Thank you very much. Thank you very much. Can I ask a very small question, very short one? The structural properties of the RC, where you integrated, the capillary pipes were integrated. That means these RC walls, are they also able to act as load-bearing elements or not?
Yeah. It was, the ones we used, that was glass fiber reinforced concrete, glass fiber short fiber reinforced, so 1 to 2 centimeter short fiber concrete, which has a certain structural stress performance, but limited. The ones which I showed from this factory building, that's a story I didn't tell. That's so-called ductile concrete. Ductile in the means of having a stainless steel reinforcement of stainless steel meshes. The interesting thing with the stainless steel, you can reduce the dimension of the concrete because of no corrosion problem. And the interesting thing with the meshes is that it allows you to have a very spread stress performance surface in the concrete, which then allows to to get this ductility of the steel mesh into the concrete as structural component. So the factory buildings, the outside wall was I think 5-6 centimeter thick, 10 meter high a concrete plate, which really starts to move when you really put it under pressure. So it it really accepts a certain movement because of this ductility. And the inner P sections, so main structure with some 2 wings, that was done in normal steel reinforced concrete, with the capillary pipes being placed on top of the reinforcement in, say, the first 3 centimeter of the concrete surface, which is the depth which was identified to be the most feasible depth for the pipes to harvest or deliver the energy. Yeah, you just you add this into concrete as a simple set. This company Rieder, which I showed very briefly, they do facade panels. Concrete facade panels in all shapes and forms and colors, and they try to integrate this into facade panels. I lost a bit track how far they are. They placed it once as a product, but I haven't seen it being installed somewhere.
Okay. Thank you very much. Thank you.
The next question is from Daniel.
Merhaba hocalarım.
From our student, yes.
I would like to thank Ulrich for the presentation and the discussion talk. I have a question regarding, I will go back to a question about the cost effective of this technology. I believe it's going to bring it so much down because, I mean, the labor intensive will be low, and also the time is also faster. I mean, you can build the house by 24 hours or 48 hours, one story, small house. I mean, isn't these things are going to be in favor of humanity?
That's an interesting question. And I have to say, I have an intensive discussion with my father about it, who's an architect as well. And he always argues, what should all these craftsmen people do when they have to use all the computers? Isn't this in favor of humanity? That's an interesting one. When we look at this generation, which grew up with their smartphones, you don't have any worries to use any digital tools. So this craftsmanship changes, which is an interesting one. Yes, the costs of these technologies are brought down intensively. Absolute. The first aluminium knot I bought, I paid 6,000 euro, and 5 years later I bought the same dimension for 250 euro, which say expresses how these things change. When we bought the very first 3D printer with Marcel, can't remember, 15 years ago, it was 50K. And if I buy the same quality printer now at the grocery shop for 300, that brings it down. So yes, in that respect, this technology will bring down the costs will be brought down by technology, and people will adapt to that technology as well. But still, other technologies are so much cheaper, unbeatable cheaper, that the 3D printing will not be the technology to do all of it. And precast concrete on site, a certain volume is really very fast. And when we see all these nice pictures of a 3D printed house being built in one day, it's a single layer. They don't have a concrete ceiling because they can't print a concrete ceiling yet, and the roof itself is something different. So this is more advertising a technology to bring this technology more to awareness, which is absolutely okay because that's necessary to express a certain technology. But don't believe that other things are impossible because of that. If you would like to do the same house in timber, you easily find a CLT manufacturer which do it in the same time slot. If you go for the bricklayer robot from Gramazio Cola in Zurich, you can have that device doing the same result in a bricklayer setup in a certain time as well. So don't see this as the only true answer. It helps a lot. Yes.
Yeah, but this is in the fact of building, for instance, in a linear way. But let's say we are building in a more organic form type of. This is like quite.
Yeah, that's another argue. Yes, the organic form may be interesting, but you also need to identify for what purpose. Gravity is not organic. Gravity is straight, rectangular to the bottom.
And
so
in our current perception, I believe, I don't know, like we see it this way, but yeah.
But gravity is.
We are held by it. Maybe it's
exactly, and it's a physical law. And expecting you build on ground on Earth, this is going to stay like this. I think you need to identify why you want certain geometries for what purpose. And yes, I agree. Our human body doesn't expect a rectangular room corner. It could be different. Absolute. I'm totally with you. And this technology helps you, or these technologies, not only printing, milling as well. These technologies helps you to create a broader variety of forms. And you're also mentally stuck in this rectangular environment. I'm absolutely fine with that. But don't try to argue it needs to be curvy because it needs to be not rectangular. You need to identify what is the purpose of what you do.
Yeah, of course. Thank you so much.
Thank you. And any other questions?
There's another one. Isn't less labor means of cheaper construction?
It's me. It's
yeah, the same student.
Yeah, but let's think about that, and let's think about that in relation to, say, your country. Often, forgive me if I'm doing wrong. Middle dimensional labor cost versus India versus Norway. It depends a lot on where you produce and where you need it. So in India, it would not make sense. When I was once in South America, I was asking them, why don't you do prefab construction? And they said, we have too much people to work. This would be asocial to do. I totally buy it. I get what they argued. When I would do the same in Norway, they would say, we need to do prefab because we don't have the people being interested to work in that environment for that low budget. And friends of mine having a steel manufacturing company in Istanbul, they manufacture for the North American market, transporting all their units to North America because, say, the technical skills of the labor in Istanbul is a high value versus the less technical but more expensive skilled labor in New York. So you do that transport. You then argue about the energy for the transport, different story. But say less labor, cheaper construction, that doesn't work in general. It does work at some places, but in other places it's exactly the opposite. And that's an interesting experience. You really have to identify where you are. So next to the climate, the, say, social costs, the labor costs, that's an important aspect to do certain technologies or to not do certain technologies. And it's not for saying the one is better than the other. It's more an experience which you identify.
Thank you, Ulrich. I think I can pass to my questions.
Okay, now I'm going to get grilled. Come on.
In March, I was at the Future Envelope conference that you organized. There were interesting papers there, and inspired by those papers, I structured my questions. Just what will be the next for the facades, especially after the pandemic? Can this pandemic specifically affect the facade industry? Can it be the other milestone in your influences diagram, for instance? Because there are basically three measures against the transmission of this virus. There are physical distancing, wearing masks, and the proper ventilation. All are adopted as effective for reducing the risks. This increases the importance of ventilation through facades. My other question is, today we definitely understood that we need to have a connection with nature. What can be the role of the facade? How can facades provide this connection, our connection with nature?
Okay, so it's the pandemic one and it's nature.
Yeah.
Okay. The pandemic as an impactor on the roadmap, that's a good idea. Thank you for that. I'm really going to consider that as an influence. I thought about the financial crisis, but that's just money. So it didn't say really change our behavior. This pandemic may change our behavior. I remember in Istanbul, when you want to go to the Asian side from the European side, you really take this decision very serious because it's going to take you 2 hours just for the bridge. So this pandemic situation where we all now learn that we can do a lot of home office work, so that we can do even conferences with our colleagues in this setup. I'm never going to fly again to Los Angeles for a 20-minute speech. It's not going to happen. And yes, if we want an interaction, we're going to organize a workshop. It's going to be a week. It's not going to happen 15 times a year, but every 2 years. So there's going to be a change. That's clear. Yes, I totally believe that we're going to have a physical university, but it's not going to be the total university anymore. It's going to be a third less, which means that our personal environments, or the places we live in, they're going to change. That's something which we clearly can track, and we also already see this in the costs of houses in the surrounding of cities. You you see a clear shift from larger cities, from people from larger cities outside of these cities. Coincidentally, I'm a bit aware of, say, how the prices developed in the region between Genoa, Turin, and Milan. Milan is one of the most expensive places in Italy, and people understand. Okay, if I can can't afford a flat in Milan, I may buy a house for the same price, an hour or two away, and I travel twice per week to the city to have this situation of physical meetings. That's going to change. So in that respect, the type of buildings is going to change, which we're going to build. They're going to be broader in mixed use. We see large companies, Deutsche Bank, for example, one of the largest banks in Germany. They understood that even 98% of their staff working at home, the system still runs. Yes, you may not do that forever, but you may do that for a limit. So that's going to change our built environment, absolutely. So I totally see that that as an aspect, and that's going to be more for multi-purpose than single purpose buildings, and that changes the building envelopes. And then the nature one, that was also an interesting experience. We had these two conferences, Future Envelope and the Power Skin, and this dealing with nature, integrating nature into building envelopes. That really became something which were addressed by a lot of speakers, some being asked by us and some just coming by themselves. And so we see that happening. Istanbul is having an intensive issue with limited green in the city. So that delivers all the positive aspects of humidity, of less noise pollution, a different color, but it also delivers a kind of a mental freedom. So this seems to be something which is interesting. We had that talk by Rudi Scheuermann from Arup, who intensively argued for this. I really liked it, but he also said urban farming he doesn't believe, because when you think about all the pollution in the city, you don't want these food to be used. So that's something where he thought like this is something different. Another one I'd like to add, which I noticed in these conferences, user interaction, user behavior. The happiness of the people using it. Sinem, this was your PhD as well. How does this influence our building envelope designs? That seems to be something which is developing as well. So I see next to all that research, I see also parameters getting into our designs to have the people more accepting the building envelopes as they are or as they're supposed to be. So this is the third thing which I would add: the pandemic, the nature, and the well-being.
I have one last question. We know facades need to be designed through the consideration of a great number of factors all at once, and facade design is given shape as a result of collaborative work by stakeholders from different disciplines. In the future, which disciplines will contribute to the architects most in this facade design process? Will they be the product designers, for instance? I mean, with whom we need to learn to collaborate?
Yeah, I'm going to give an answer. Sime did a PhD about what are the influences of facades to a certain function, in her case schools, and investigated the design process, decision-making process, the arguments which are influencing. We learned that, say, out of history, structure design was an important aspect. Building physics is an important aspect. Climate design is an important aspect. We now talked about nature and user behavior as aspects, and the product designers are going to supply system solutions. So you have a system supplier who supplies a system, and that's what the product designer does. The architect who has the opportunity to design a one-off building envelope, they need to identify what technologies are most feasible for them, for what they want, and then come to this decision to choose the right engineers for their situation, to convince the client to pay them, and then develop it. So there's no yes or no answer in the one or the other direction. It depends on what project you're dealing with. So if it's say a mainstream project, then the product developers are going to be interesting, no question. If it's an individual project, a very individual project where you're able to develop individual systems, which means it has to have a certain size, then you're mainly going to orient yourself towards the engineers supporting you in your design, as long as you're not the engineer yourself. But it's not going to be black and white.
Yeah.
Luckily.
Thank you very much. If we do not have any more questions, then I would like to thank you again for being with us. And I would like to give the words to Mine Hoca. We are coming to the end of today's ArchiDesign Talks, and thank you for your attendance and valuable contributions. Mine Hocam.
Professor, we want to really thank you for this stimulating presentation. It's been great having you with us. We have a little tradition here in ArchiDesign Talks. As Bahçeşehir University, Faculty of Architecture and Design, we make a small donation in our guest's name. So now you have 3 young trees in a memorial forest in Turkey.
That's a good one. That's a good one. The normal donation was a kind of glass box or something. I like this one. This is good, and it gives me an argument to come to Istanbul. And you have to show it to me then. You have to find them.
Thank you so much for all your time and effort.
Yeah, you're welcome. You're welcome.
Thank you, really. Thank you for your valuable time. I hope we can host you in person as soon as this pandemic process come to an end. This is our wish from our hearts. Please take care of yourself.
Same to you. We have this strange word now in the Netherlands, stay negative.
Yes.
Yeah.
Very much.
Yeah. Instead of take care.
Exactly. Stay negative. Yeah, thank you for inviting me. Thank you for pushing this scene. This was nice and also interesting. And as I said, I really miss Istanbul. So.
Yeah. Thank you once more. It's great to see you.
Okay. Good evening, everybody.
Good evening.
Bye-bye.
Good evening.
Bye.